Alright, so in this video we're going to talk about the different types of numbers we'll be seeing in algebra. I have a diagram here for these numbers and I'll go over each of these sets briefly. So in this diagram here you'll see that each set of numbers includes the sets of numbers below it. So for example, an integer is also a rational and real number, possibly a whole number, a natural number, we're not sure, but it's certainly not an irrational number. This might not make much sense now, but once we get into the details, it'll make a little more sense. So let's start with the most specific type of number set we have here, which is the natural numbers. Natural numbers are also called the counting numbers, which makes sense since they're the ones you use when you're counting 1, 2, 3, 4, and so on without stopping. That's what these three dots here called an ellipsis means. It means that they go on and on. There's no end to the set of numbers. 1, 2, 3, I'll plot them over here and on. That's what this arrow means, on to infinity, which is another way of saying that if you want to count these numbers out, you wouldn't get to an endpoint because they go on forever. And then whole numbers is the next set we have, and they're just the natural numbers with 0 added into it. So that's 0, 1, 2, 3, 4, and on to infinity. So that's the same thing here with 0 added on the number line. And now integers are whole numbers, but also the negatives of those numbers included. And they go on and on in both directions, the positive and the negative. So they are from negative infinity through 3, negative 2, negative 1, 0, 1, 2, 3, and on to positive infinity there. So we can chart those out like this. And those are integers. Now rational numbers aren't quite as intuitive. I can't plot these in nice little dots and arrows on this number line here. But what rational numbers basically are is they are any number that can be expressed as a quotient of two integers. Any number that can be expressed as a quotient of two integers, which also means that it can be represented as a fraction. So if we have two integers, integer a and integer b, that means that a can be anything and b can be anything except 0. So you can't divide by 0 obviously, because that would be undefined. But b can be 1, which means that any integer is also a rational number, because if you take any integer and divide it by 1, that's the same thing as itself. So that's represented as a fraction there. That's 4 represented as a fraction. So it's an integer and a rational number. So rational numbers would be like 3, 0, negative 3, and typical fractions like 5/2, 2/3, 1/7. All those are rational numbers because they're fractions. But decimals are also rational numbers because they can be expressed as fractions. So 0.2, negative 1.7, 5.4321. Any number, any number with a decimal that ends or has a repeatable pattern. So because you can see that these numbers can be expressed as fractions. 0.2 is just 2/10 or 1/5. Negative 17/10, 54,321 over 10,000. All those numbers can be expressed as fractions and therefore are rational. So those are the rational numbers. Now I'll skip over irrational numbers for now and focus on the real numbers, because that will give us a little more insight into what irrational numbers are. So real numbers are any numbers that can be plotted on this number line here. And since this goes on and on, that's any number between negative infinity and infinity. So that's pretty much anything you can think of. And what real numbers are they're either rational or irrational. There's two types. And so irrational numbers are therefore real numbers that aren't rational. So what that means is irrational numbers can't be expressed as a fraction. So some examples would be square root of 2, which is approximately 1.414. This is just an approximation. This can't be put out into a decimal. This keeps going on and on. So therefore, it's irrational. Likewise with pi, which is just approximately 3.14. This keeps going on and on. This is just an estimate. Therefore, it is an irrational number because it can't be expressed as a fraction. Alright, and then there's this other set that's off by itself, the imaginary numbers in its little bubble there. Imaginary numbers do exist, but they are different than real numbers. They are separate than real numbers. They have to do with I, which is equivalent to square root of -1, which can't be expressed as in the real number world, so they're just imaginary numbers. Don't worry about them too much. I probably won't even cover it in my series, possibly though, but they're more of an Algebra 2 thing. So with that being said, we have all the types of numbers. Let's do some examples to really hammer what we got here. Hammer it in. So the colors that I'm using here for these don't have to do anything with these. Like this one's not an imaginary number, obviously. Just go with the colors. So 1 is, if we want to classify it, we'll look at each set and see if it is a true statement, and then we can move on to the next one. It's a true statement. If not, we can just stop. So if we find that a number is real, rational, and integer, but it's not a whole number, and we don't have to keep going on to see if it's a natural number. If it's not a whole number, you just stop and say it's integer, rational, and real number. Okay, 1 is a real number, can be expressed on the number line, plotted on the number line. 1 can be expressed as a fraction. It's an integer, it's a whole number, and it's a natural number. But we could also just said 1 is, since it's a natural number, 1, 2, 3, 4, 1 is included in that. We could have just said, since it's a natural number, it is also a whole, integer, rational, and real. But that's what 1 is: real, rational, integer, whole, and natural number. Next example, let's do -4.2. -4.2 can be expressed, or can be plotted on the number line. It'd be about right here if we put it -4 there. So therefore, it is a real number. It is rational, since -4.2 would be just -42/10 or -21/5. But so it can be expressed as a fraction, so it's definitely rational. But it is not an integer because it would have to be on one of these little points here, one of the dashes. So that's what -4.2 is: real and rational. So next example, we'll do 1/3. 1/3 is a real number. It would go about right here. It is a rational since it is a fraction, although one might say 1/3 is approximately 0.333, but this 3 goes on and on, so one might say, hey, it's just it's a decimal that keeps going on and on, just like pi, which keeps going on and on. Shouldn't it be rational? But since 0.3, since 1/3 is 0.3 with the 3's repeating, there's a pattern to this, that it's all 3's, and it can be expressed as a fraction. Therefore, 1/3 is rational. Of course, we know that since it's a fraction. But I thought I just might put that in. So it's 1/3 is real and rational. And the last example we'll do is square root of 7. Square root of 7 is real, of course. It would be put somewhere in between 2 and 3. Not quite sure, but in there somewhere. But unlike the other ones, this is going to be irrational since it can't be expressed as a fraction. Radical 7 would just, if you put it out as a decimal, it just keep going on and on without a pattern. Just like what square roots do, they go on and on without a pattern unless they're happen to be a perfect square. So like square root of 4, square root of 9, anything that has a square underneath the radical, perfect square underneath the radical, would be rational, but otherwise square root is going to be irrational. So that's what we have here for this video. I hope you guys found it somewhat useful, and I'll see you guys in the next video.